Good afternoon again, ladies and gentlemen. I am Salifu, as is said, and I'm also a PhD student at UNESCO IHE. My main research topic is on fluoride removal from groundwater. I work in Ghana, and in the area where I work, we have problems with with fluoride in the groundwater. And my research is on fluoride removal from groundwater. But alongside that main objective, we thought it was also interesting to try to find out or to explain what is causing the fluoride occurrence in the groundwater to start with. So this presentation is based on that. Now, I'll just briefly give some kind of background to this study, and then the motivation and objectives, and then the methodology that I used in the study, and then the results that I got, and some conclusions. Ghana is in West Africa, and the northern part of Ghana is where I work. And in that area, we have the fluoride problem in the whole region, in the whole of the northern region, but it's more prominent in the eastern part of it, and that is what I've highlighted over there. It is made up of about 11 administrative districts covering an area of 27,000 kilometers with a population of about 1.1 million, and it's a very rural place. And like many of the people have indicated, about 95% of drinking water source in that area is based on groundwater. Now, somewhere in 2001, we noticed the presence of fluoride in the groundwater in that area. So our first attempt was to try and treat it. Now, the picture you see, is it on this left here? On this side is a groundwater borehole which is contaminated with fluoride, and we tried treating it. So the system that you see there has iron oxide coated sand, which we were trying to use to treat the fluoride. Unfortunately, we were not successful, and we had to close that well down. And we have many boreholes that we have had to close down because of the fluoride problem. And that is a drain to our national economy, because drilling a borehole will cost about $5,000. So if you drill and you have to close it down because of fluoride, then it's a drain to the national economy. At the same time, it is also hampering our progress in providing water to the rural communities, because you get the groundwater for them and then it has fluoride, you have to close it down. And coupled with that, is the prevalence of water-related diseases that is typical of in the area that I work. Now, the other picture over there shows the inadequacy of water in that area. So if you get a water source and you have to close it down because of fluoride, it becomes a problem. Now, fluoride has health effects. If you take fluoride in reasonable quantities mean 1 milligram per liter, it is good for dental health. But if you take fluoride for long periods with concentrations beyond 1.5 liters per milligram per liter, then you start having health problems, which ranges from fluorosis to loss of mobility, lowering of IQ of children, kidney problems, and even death if the concentrations are very high. Now, the major source for fluoride ingestion is mostly through drinking water. Now, these are some pictures that shows the effect of ingestion of or drinking water with high fluoride content. The lady at the top there is just about 40 years old, but because of the fluorosis, you see, she's almost looking like she's 80. Now, what is making us interested in trying to find out what is causing the fluoride occurrence is that, like I said earlier on, 95% of our water sources is from groundwater. But unfortunately, we have little knowledge about the groundwater chemistry and also what is actually causing the fluoride occurrence in that area. So the objective of my study was to study the geochemical processes that is influencing the groundwater chemistry in that area, and to also to try to explain the genesis of high fluoride in the area. Now, the methods I used for this study was to sample groundwater from that area. I picked samples from about 350 boreholes and analyzed for some chemical parameters, which include fluoride, bicarbonate, calcium, sulfate, and nitrate. Then I did basic statistical analysis of the chemical data. Then I also used Piper diagrams or Piper classification to try to determine the groundwater types in the area. Then I also used principal component analysis. Now, principal component analysis is a tool that is used in various fields, and it's in the groundwater area. It can be used for studying, analyzing groundwater data, and it can give you an insight into the geochemical processes that is happening in an aquifer system that is influencing the groundwater chemistry. Now, these are the results that I got from my study, the basic statistics. Now, you see pH ranges from 6.1 to 9.5, fluoride about 0 to 11.6, sodium 1.3 to 1,021. So if you see these figures, you see that there's a huge variation in the water quality in the study area. Now, from the study, it came out that 25% of the sample that I had fluoride values below 0.5 milligram per liter. And people who consume those type of water may have dental caries. Now, 52% were okay. That is, they had concentrations between 0.5 and 1.5 milligram per liter, which is what is required by WHO standards if you don't want to have any problems. But then 23% were beyond the WHO standard, and people who consume that are at the risk of fluorosis and the other diseases that I described. Now, if I do some projections based upon the percentage that has the fluoride above 1.5 milligram per liter, then in that area, about 154,000 people are at risk of getting health effects from drinking the water that they are drinking. Now, these are some pictures that I took in some of the communities when I went for my field work in Ghana, in some of the communities where they are consuming water that is beyond, that has fluoride beyond the accepted value. The top there, you see people with young guys with dental fluorosis, and then below you see skeletal fluorosis. Now, apart from the health effects, this also has some social problems, because normally the young girls and the young men with this kind of teeth, they find it a bit difficult getting wives and husbands because of the way their mouths look like. Now, from the Piper diagram, which I used to analyze my groundwater samples, it came out that there were 6 groundwater types. So many groundwater types. That also indicates how variable the water quality is in that area. And that also gives an indication of, it gives an indication that there are so many processes happening in the aquifer system, resulting into various types of groundwaters. Now, what is also, I have no pointer here, but if you look at this Piper diagram, you see that most of the samples plot in an area that indicates the predominance of sodium bicarbonate type of water, and that has implications with fluoride occurrence. Now, this is the results of the principal component analysis that I did. Now, the principal component analysis, what it does is to reduce data dimensionality. So I had, on this side is the original groundwater parameters, but this about 13 parameters were reduced to 4 principal components. Now, the principal component analysis, it reduces the data dimensionality and it makes it a bit more easier to interpret. Now, the principal components, which is principal component 1, 2, 3, and 4, can be interpreted in terms of water-rock interaction, depending upon the weights. The figures that we see in there are component weights, and they relate, the component weights relate the original parameters to the principal components. So if you take, for example, principal component 1, we see that it has a high loading for calcium, and then magnesium, and then sulfate. I tried to highlight that. And based on those loadings of those parameters on principal component 1, you can interpret it in terms of water-rock interactions or geochemical processes that is happening in the aquifer system. Now, I've tried in 2 small slides to split the table into 2 to ease to help maybe with the explanation. So if you take principal component number 1, like I said, it has high loading for calcium, magnesium, and then sulfate. Now, the interpretation of that is that it indicates mineral dissolution. That is the dissolution of gypsum and then dolomite in the aquifer area, giving rise to those parameters dominating that component. Now, if you take principal component number 2, it also has high loadings for sodium and then chloride. That is also a reflection of the dissolution of halite, that is sodium chloride, in the aquifer materials, dissolving to get sodium and then chloride into the groundwater system. And it also indicates sodium-calcium ion exchange processes. So these 2 components give some indication of some water-rock interactions or geochemical process that is happening in the aquifer system and then influencing the groundwater chemistry. But what is also interesting here is that fluoride shows a positive loading on principal component number 2, which also means the processes that is happening or associated with principal component number 2 also promotes the enrichment of fluoride into the groundwater system. Now, if you take principal component number 3, it also has high loading for bicarbonate and then sodium and pH. I don't have a pointer to show you. And that's also a reflection of the dissolution of carbonate minerals, and then also cation exchange processes involving calcium, magnesium, and then sodium. Now, principal component number 4 also has positive loadings for potassium and then pH. That also is an indication of mineral dissolution and also the consumption of hydrogen ions in the groundwater system, which gives rise to the potassium and then the high pH. Now, what is also interesting here is that fluoride shows a positive loading for principal component number 3. Now, based upon the positive loading of fluoride for principal component number 2 and number 3, principal component number 3, it makes it possible to have an insight or an indication as to what processes are happening in the groundwater system that is giving rise to the fluoride enrichment. Now, the loading of fluoride on component number 2 and component number 3 suggests that the processes associated with component number 2 and component number 3 also enrich fluoride. Now, if you take principal component number 3, the processes associated with it makes the processes associated with principal component number 3 gives rise to the predominance of bicarbonate. And the bicarbonate in the groundwater system causes calcium carbonate to precipitate. And in the process of the calcium carbonate precipitation, it takes calcium itself from the groundwater. Now, that is a favorable condition for the dissolution of fluoride. Fluoride is the main mineral that usually dissolves from the aquifer matrix and then releases fluoride into the groundwater system. So if there's any process that brings calcium out of solution, it enhances fluoride dissolution. So the processes that with PC3 or component number 3 that brings about the bicarbonate predominance gives rise to the precipitation of calcium carbonate and favors the dissolution of fluoride. Now, in the same way, the sodium calcium ion cation exchange that is also happening in the aquifer system also depletes calcium from the groundwater, which in turn favors the dissolution of fluoride, and for that matter, fluoride enrichment. Now, the third mechanism is that fluoride shows a high, shows a relation with pH. That also suggests that fluoride gets into the groundwater system from the aquifer matrix through fluoride OH anion exchange. I think the OH should have been plus. Should have been minus. So in a nutshell, these are the processes or mechanisms that is causing the fluoride enrichment in the groundwater system. Now here I have tried to plot. This is the geology of the region or the study area. That is the northern region. I have tried to plot the fluoride to show the fluoride occurrence in the area. The red dots that you see there are fluoride occurrence, and the size of the figures, the size of the dots shows the concentration of the fluoride. So in conclusion, from my study, 23% of the groundwater samples were beyond 1.5 milligram per liter, and those who are consuming that water are at risk of fluorosis. And then the factors that is influencing the fluoride enrichment in the groundwater system has to do with calcium depletion through calcium carbonate precipitation, and then also calcium depletion through sodium calcium cation exchange, both processes which influences or favors the dissolution of fluoride into the groundwater system. And then the third mechanism is the fluoride OH anion exchange. Now, I think that this study can help in planning for water supply programs in the area in terms of finding other alternatives for places where there is high fluoride, and then for places where there is low fluoride below the requirement. So that brings me to the end of my presentation. Thank you. And I wish to acknowledge the UPRAF project in the UNESCO IHE who are the sponsors of this work. And then also when I went to Ghana for my field work, the organizations that helps me. And then my supervisor is also here, Dr. Petrusevsky, who is supervising this work. Thank you.